Thank you and welcome today once again. If you are new here, please hit our subscribe button and hit also the bell to get more educative videos from mathematical solutions. So today we want to do a given proof under statistics, where we want to prove that the sample variance S squared is a biased estimator of the population variance sigma squared. We need to show that the expected value of S squared is not equal to the population variance sigma squared. We have two types of estimators. We have a biased estimator and also an unbiased estimator. When we say an estimator is biased, we mean that the expected value doesn't give us the population figure they are representing. In this case, we have the sample variance and the population variance. So the expected value of the sample variance, we find that if it's not equal to the population variance sigma squared, then we say that the sample variance S squared is a biased estimator. But if we can prove that S squared, expected value of S squared is equal to sigma squared, the population variance, then we can end up and say S squared is an unbiased estimator. So let's go on to our presentation today. We want to prove that S squared is a biased estimator of sigma squared. Proof. Here, expected value of xi is assumed to be mu, as long as the population mean exists. The variance of xi is equal to sigma squared. I is equal to 1, 2, 3, all the way to n. Then, S squared, from the general knowledge of statistics, we found that S squared is equal to the summation of xi minus x bar squared divided by n, where I lies between 1 to n. Then, having that, we want to introduce now the population mean, mu, in form of a 0. That means we put a negative mu, then we also add mu. There's nothing that will happen to that thing. It will remain as 0. So S squared is equal to the summation from I is equal to 1 to n, xi minus mu plus mu minus x bar squared all over n. Grouping them into two, we have S squared is equal to summation from I is equal to 1 to n, where xi, we have xi minus mu minus x bar, everything squared, all over n. Then when we expand xi minus mu minus x bar squared, we get S squared is equal to summation from I is equal to 1 to n of xi minus mu, everything squared, minus 2 in bracket xi minus mu bracket x bar minus mu plus x bar minus mu, everything squared, all over n. S squared therefore is equal to summation from I is equal to 1 to n of xi minus mu squared over n minus 2 summation of I from 1 to n xi minus mu bracket x bar minus mu all over n plus the summation of I from 1 to n of x bar minus mu squared all over n. S squared is equal to summation of I from 1 to n of xi minus mu squared all over n. So we have introduced an n there, because summation of I from 1 to n, so we multiply that thing by n will give us the same thing. So it's 2n in bracket x bar minus mu bracket xi minus mu. But summation of I from 1 to n of x bar minus mu square all over n is equal to summation of I from 1 to n of x bar minus mu times x bar minus mu all over n, which will have n x bar, n bracket x bar minus mu bracket x bar minus mu is equal to n x bar minus mu squared. That's mu squared. Therefore, s squared is equal to summation from I is equal to 1 to n of xi minus mu bracket s bracket is square everything over n minus 2n in bracket x bar minus mu squared all over n plus n x bar minus mu or squared all over n. The two on your right hand side are like terms, so you can just add them together. What we'll end up and say the 2n minus n, 2n minus 2n plus n gives us minus n. So the final result on the right hand side is minus n x bar minus mu squared all over n. But summation of I from 1 to n of xi minus mu squared all over n is the population variance sigma squared. This implies this: s squared is equal to sigma squared minus n x bar minus mu squared all over n. Thus, the expected value of s squared is equal to sigma squared minus expected value of x bar minus mu squared. Hence, expected value of s squared is not equal to sigma squared. Then, what is the expected value of x bar minus mu squared? This is the same as the variance of x bar. And how do we write x bar? X bar is like sample mean. So the summation of x or summation of xi from I is equal to 1 to n over n is the same as x bar. So when we remove n outside, it will be n squared. Then the variance is equal to summation of variance of summation of I from 1 to n of xi over n is given by n over n squared sigma squared, which when you simplify you get sigma squared over n. So our final results, we got that sigma squared is not equal to sigma squared minus sigma over n. Hence, s squared is a biased estimator of the population variance sigma squared. And what is the type of biasness? Here we have a negative biased estimator. That is how we can prove that the sample variance s squared is not an unbiased estimator of population variance sigma squared. Thank you for watching. Please feel free to subscribe to our channel for more educative videos. Mathematical Solution is the home for all mathematical problems in the world. Thank you.